Hello, everyone. It's great to be here. I'm Alexis Gallagher. I'm the CTO of Topology Eyewear. And today I want to talk about machine learning, but from the point of view of a Swift developer or an iOS developer who may not have encountered it before. At Topology Eyewear, we make personally customized glasses. And we take a video of your face, and then from this video, we use computer vision to build a detailed model of the shape of your face. And then based on that model, we're able to present an augmented reality view of what different kinds of glasses would look like on your face. You can choose the color, the design, the size. My nose isn't quite straight, so it's good because the model isn't quite straight and the glasses are exactly fitting my nose. Because we use all that information then to take Italian acetate plastic, which is what's used for premium glasses elsewhere. And then it goes into this very impressive manufacturing robot, which I'm told I shouldn't show the inside of because those are our secrets. And we use the information then to make a 100% customized pair of glasses. Now to do this, I said we use a lot of computer vision code. And that's true. And for a while, I kept hearing about machine learning, and it seemed like hype, because there was so much talk about it, and artificial intelligence is never as magical as people say. But then I realized, and it felt silly not to realize it at first, that actually most of computer vision now involves machine learning. So I've been working at a machine learning company without knowing it. I felt silly, but it's true. And why is this possible? Because machine learning is changing so fast that it's easy to lose track of it. And you can ask the question, what is machine learning really? What is it if you're not reading a newspaper, but you're a technical person and you want to know what it really is? So here is a very simple, but I think accurate definition. If you think about it, most of the programming we do involves human thought. When you're defining a function, there is a moment of human analysis and thinking, and then that gets turned into the function. Machine learning just means when you define a function, not by human analysis alone, but with a big pile of data. If you're using data to define your function instead of just human thought, you're doing machine learning. Simple as that. Here's a really simple, trivial definition just to drive the point home. Let's say I wanted to make a function that would predict how tall a person is. Here's a terrible way to do it. I could measure the height of everyone in this room. Everyone in this room would be called the test set. I could then take the average of all the heights that I've measured. That's our machine learning model. We're just taking an average. And then I'm going to write a function that does nothing but return that average. That's called executing the model. That's a machine learning model. We've taken data and we've used it to define a function. Obviously, it would be very bad. It's not going to give the right height for most people. We can measure how bad it is, and that's what you'd call the error. We could make it a little better. I could maybe measure the heights of all the women in the room and then measure the heights of all the men in the room, and then my function would take the sex of a person we're trying to predict, and then it would give different values depending on if it's a man or a woman. That would be a slightly better machine learning model. Or if we wanted to get yet more complex, I could measure everyone's age and weight and shoe size and a number of other things, and I could find a set of coefficients that I would multiply against all those things. So I'd take your age and multiply it by one coefficient plus your weight by another coefficient, do that out for a bunch of variables, and use that to predict your height. Still probably not the best model in the world, but it would start to get better. If you have big shoes, you're probably taller. Of course, what I'm describing is a linear regression. Sorry. What I'm describing is a linear regression. And linear regressions are not new. We've been doing them since the late 19th century. They were invented by this fellow, Francis Galton, who invented the linear regression while he was studying sweet pea flowers and trying to see how tall they would be. So if none of this is actually new, if we've been doing linear regressions and defining functions with data for a long time, why is there all the excitement and conversation about machine learning right now? Well, there's a couple reasons. There's a sort of boring reason and an interesting reason. The boring reason is that right now we have a lot more data than we used to have because of smartphones and because of the internet and how they help us gather data. And we have a lot more compute power, so we can just do the things we used to do with more data. And then the interesting reason why it's exciting is that when you apply a lot more data, some of the kinds of models we're building are working in ways that end up being surprising. So the classical example for this is neural networks. So this is a simple neural network. There's 3 input cells that represent sort of imaginary neurons. There's 2 output cells and 3 in the middle. So that's a total of 9 variables. You put some values in the beginning, you get values in the end. You can think of the 3 layers as working like function composition. These have been around since the late 1950s. They did not always produce super impressive results, and work on them was not very prominent and moved slowly for a while. But what happens if instead of having 3 input variables, we look at every color channel for every pixel of an image? And what happens if instead of having 3 layers, we have 48 layers? And then what happens if we train this on thousands and thousands of different images? If you do something like that, you end up with a network like this. This is a diagram of the structure of the Inception version 3 neural network, which is one of the best networks for classifying an image. You put an image in the beginning, and then in the end you get a declaration on what kind of an image it is, one out of 1,000 possibilities. In fact, Apple at the last WWDC provided sample code that you can use to run Inception on iOS devices and run it in a very efficient way with GPU optimized implementation. Here you can see I've taken a picture of a bottle, and then it's told me, yep, that's a water bottle. And you might want to guess why it's guessing it might be an oxygen mask with 1%. The reason is that I took this picture on the airplane, and I think the picture spotted other things that look like they're in an airplane, and from that it guesses, well, there are oxygen masks on airplanes. So it's sort of cheating, but that's how it comes to these inferences. That's kind of the boring part. You just have more data, more numbers. What's interesting and a bit magical about these networks is that the way they work. If you look at what's happening inside the network, you can see that the different layers represent successive layers of abstraction. So at the bottom you're putting in colors, and then a layer, the next layer, finds edges, and then the layer after that uses the edges to find shapes, and then a layer after that recognizes different objects. So it's a little mysterious that when you're trying to teach it just to classify 1,000 things, you actually end up teaching the network how to see in a more basic way. And I think that result's kind of surprising. So if I just sort of summarize why people are excited about this sort of work right now, one way to think about it is this funny comic from XKCD. So this comic was published in 2014, and the joke is sort of, some things are very hard in computers. Like if you want me to tell you if there's a bird in a picture, I need a research team to do that. And that was probably true in early 2014. But now in 2016, you could probably build this in a few days by taking the Inception network that's already been trained and training it a little bit differently in the last layers just to pick out birds. So that's progress, and that's kind of cool. And we're living through a time now when neural networks and other kinds of deep learning, machine learning models are breaking through benchmarks that have been sitting around a long time, not just in image classification, but also in speech recognition, speech synthesis, other areas as well. But this is a Swift conference, and the question is, as a Swift developer, like why do I care? What is this relevant to us? As a Swift developer, a number of questions you might ask. So one question is, does this affect me? Does this affect mobile application development, let's say? I'd say the answer is yes. And the reason is that machine learning, although it's now maybe trendy and new, it's soon going to become very boring and very everywhere. If you think about it, there's all sorts of systems that are already using it. Predictive typing on the keyboard, spam detection, face recognition, OCR. These are all earlier machine learning systems, and we're just going to see more. There's going to be more opportunities to automatically process documents, automatically comprehend images. It'll become like media encoding. There was probably a time when it was difficult to decode audio from a file. Now it's just a one-line call to handle an MP3. I think machine learning is going to be provided by our platforms and vendors. But that doesn't sound like much fun. You're probably wondering, well, could I build my own machine learning model, even if I'm not a mathematician, even if I haven't spent a long time studying these things? And I'd say the answer to that is also yes. really the state machine learning is at right now reminds me of Swift version 1.0. When Swift version 1.0 came out, it had language features that were a bit unusual in mainstream languages. And so for a moment, you had this feeling like that people who'd studied very strange languages had heard of things like algebraic data types, which are like Swift enums. But because so many people paid attention to Swift, and because it was so important, very quickly there was a lot of educational material about it. And features of Swift that used to only belong to special esoteric languages suddenly became mainstream features, and you wouldn't think of it as an esoteric thing anymore. And I think that's a bit like what's happening with machine learning right now. It was a creature of university departments, but there's a lot of momentum behind it right now, which is focusing attention on it, and a lot of great people are being involved in explaining it. One example here of the momentum is Google's TensorFlow project. It's under active development. It's very well explained. It reached version 1.0 just a couple weeks ago. They had a summit with videos, and you can go watch the videos and get a sense of what it can do. And there are also people, public explainers who do a very good job of making these concepts accessible as something you can use, even if you don't define a network from scratch yourself. You can adapt other tools that have been given to you. But again, this is a Swift conference, so one question would be, okay, I could use TensorFlow, but can I do machine learning in Swift if I want to build my old model? And the answer there is sort of. There's sort of two phases to any machine learning system. There's defining the model and training it. That's one phase. And then the second is deploying it and using it. So if you're building a model right now, the reality is you should probably be doing it in Python. And I would think you should probably also be doing it in TensorFlow. Python is used because Python's widely used in scientific computing. So TensorFlow and many other libraries just assume that you're going to operate in Python. That's the best interface to the system. And also in those systems, you can find predefined models. You don't start from scratch. You take a model like Inception that's already there and only make adjustments that you need to. And you bring your own data and train it for the problem that you're trying to solve. When you deploy it, there's an opportunity where you could use Swift. So right now, for instance, you could take a TensorFlow model and bundle the TensorFlow library directly into iOS. Or you could host it on a server, and then you'd just be using Swift to call a web service that you built to talk to TensorFlow. You could also use technology Apple has given. Apple provides the Accelerate framework and the Metal Performance Shaders framework. And both of these provide primitive building blocks for building neural networks and other machine learning algorithms. So you can manually port a model into Swift using these libraries if you want maximum performance or maximum control over what you're doing. Metal Performance Shaders is the way you can get real-time inference from the Inception network on an iOS device. Another question you might have, just to get a sense of it, is a bit more amorphous. What's it like? What's it like to work on machine learning problems? On a programming level, it's surprisingly like programming with AVFoundation or with Core Image, because all three of these systems, TensorFlow, AVFoundation, and Core Image, they all have a deferred execution model where you're defining an object called a session or something like a filter, and you're wiring up all the pieces, but nothing actually happens until you push the go button. With AVFoundation, you might wire up a camera input to a capture session. But with TensorFlow, you are wiring up very primitive operations like adding this matrix to that matrix, or adding a convolutional layer if you're working with a higher level API for it. That's sort of what it feels like in terms of actually using the APIs. Another way I describe what it feels like is that it's surprisingly similar to developing a user interface design, in the sense that it's imprecise. One way to think about this is in terms of unit tests. Imagine you had a code base that worked 95% of the time, and 5% of the time it failed. And you couldn't really explain why it worked when it worked. And you couldn't really explain why it failed when it failed, because it was just too complicated to understand. If I said that's what your code base was like, you'd say that's a terrible code base. But if you were talking about a machine learning model, you might say, that's a great machine learning model. That's the best we can do. So although there's a lot of mathematics that goes into defining these models and how they fundamentally work, their outputs are hard to interpret, and so you manage them in the same ways you manage a software process, like user interface design. You could have a design for a user interface. You might have a hunch that this is the right way to do it, but you don't actually know if it's any good until you put it in front of users and test it. And when you put it in front of users and test it, you might find you have a great design, or you might find you don't, but there's no way you could know ahead of time if it was any good. The machine learning models are like that as well. I think that machine learning is a natural technology to be deploying on iOS, because if you think about what's fundamentally happening, these models are good for dealing with input that comes in and is a bit vague. It's not like when someone fills out a form and they say yes or no, or they give a precise number. It's someone capturing an image, maybe an image of their face. And everyone's face is a little different, and it has soft edges, and you have to deal with different kind of lighting and contours. The world around us is not full of rigid, logical, geometric forms. It's full of amorphous things, blobby things like human bodies. And because iOS devices are what people actually interact with directly, you're actually putting your finger on the device or taking an image with the device. The iOS device is what's in direct contact with the blurry, blobby quality of the world. And machine learning software is the software that's able to take amorphous inputs like that and translate it into something that's more rigid, a specific classification instead of a giant pile of pixels. This is essentially how we're using it at Topology Eyewear. We start with something very human and amorphous, a human face. What could be more specific and individual? But it needs to get turned into very precise instructions for how a robot or a laser is going to cut through Italian acetate or metal. And iOS is where the amorphousness of the world enters the system, and machine learning is where we take that and turn it into something exact. Another question you might have is, where do I start? Let's say you want to look into it. The good news is, right now, it's very easy to get started. Nobody is an expert on a method that was invented a year or 2 years ago. You can jump right in and very quickly, I think, be working with cutting-edge technology. And as I mentioned, there's a lot of resources online to get started. The TensorFlow tutorials and Summit videos are excellent. There's a Stanford Coursera course, Introduction to Machine Learning. There's a gentleman named Siraj who has fun, crazy videos on YouTube where he shows a lot of simple projects that you can put together with just a few lines of code. There's also a book, if you really want to dive into the depths of it, called Deep Learning. I think all of these are good places to start. To summarize, I'd say yes, there's a lot of hype around machine learning, but I'd say it's real. It's not just hype. The significant advances are happening right now, and it's something anyone can get involved in. It's probably coming to all sorts of APIs near you very soon, so it can be something that you'll be consuming easily, and it's something we'll take for granted. But if you want to go deeper into it, if you want to define your own models, that's something you can completely do. If you're the kind of person who thought it would be fun to learn Swift when Objective-C was completely available to you, then I think you're definitely the kind of person who can dive right into using TensorFlow or machine learning models right now. It's as approachable. If you actually want to deploy one of these things, you're going to be probably using Python to build and train models. But there's a lot of opportunities to use Swift in interesting ways to put those models literally in people's hands. That's my take on machine learning if you're looking at it from the perspective of an iOS developer working with Swift.
So with your example at the start of your talk, how you did the your glasses, so was that all being rendered on the server and then brought back down to the phone?
So what we do right now is we do the inference of the shape of the face on the server. We do calculations on the server on AWS, and then we send the results of that computation down to the phone, and then all the rendering happens on the phone. So we're using SceneKit to render the eyewear, and then we're compositing that on top of the image of the person. So it's all live, and you can have a very fluid experience doing it. But we're looking into moving more of it onto the phone. We could possibly move all of it onto the phone. And one of the benefits of neural networks in particular over certain other machine learning algorithms is that in addition to getting good accuracy, they're also more efficient for compute. So you can do things on the phone that you would need to do on a server otherwise.
That was great. Thank you so much.
Thank you.